All right, everybody. Thank you for coming. We're going to be holding a review session for the second exam. So the topics that we're going to be covering are the Fourier series, Fourier transforms, convolutions, and block diagrams. And if we have time after we finish those, we'll review some of the homework 3 concepts and stuff as well. So let's just jump into Fourier series right off the bat. So for Fourier series, we have two different equations, the synthesis and analysis equation. And we're able to utilize these equations to determine the Fourier series coefficients given an equation and vice versa. And this basically decomposes our signal, x of t, into a lot of weighted cosines and sines. So once we have the coefficients for a given signal, we can use the properties table, which is this, to determine what new coefficients will be when we transform the signal. So for example, if we take our x of t and we apply a time shift to it, instead of having to go back and do our full Fourier series synthesis and analysis, we can use our properties table to determine what our new values will be. And then we're going to jump. Do you want me to, sorry, Amelia, do you want me to do the Fourier transform stuff as well?
I can do that. I can do that when we get there.
Okay. So we're able to use this properties table to determine new coefficients when we shift, when we transform a signal. So let's go ahead and address this problem. So we have a signal x of t, which is periodic with a fundamental period of omega naught equal to 4, and with Fourier coefficients given by that equation. So now using our properties table, can we calculate new coefficients for the following cases for k is equal to -2 and 1? And then we're given two transforms of our signal. So let's go ahead and jump into this. Oh, sorry. So this is our problem statement as on the slides. So now, how can we take our values and compute new values for them? So the first thing we want to do is we want to determine what transforms are being applied to our signal. So let's start with case A. We have x of 7 minus 2t. So can anybody in the chat or just shout it out determine what properties from our series properties table are we going to use given the transformations that were done to this signal?
So it would be a shift, and then it would be an scaling.
Yep. So we have a time shift. We have a time scaling. Missed my C. And we actually also have a time reversal, because we have a -2t. So now that we've identified what transforms are being done, we can go to the properties table. Do y'all have easy access to a properties table? Give me a thumbs up, thumbs down. It should be on the slides for this, or from lecture slides.
Should we get the lecture slides 8 for the
Yeah, so let me double check. I believe they're in lecture slides 8, but let me pull up quick.
Yeah, they're in the lecture slide 8.
Okay, so take a look at lecture slide 8, and we can see the properties table there, or pull up the slides from this presentation under the recitation module on Canvas, and they're also posted there. So we've identified our 3 transformations we've done to this signal. Now, how do we evaluate what our new AK values are going to be? So for time shifting, from the table, we're given for a signal of x of t minus t naught, the coefficient is going to become a sub k e to the minus j k omega naught t naught. And if you're looking at the table, you'll see that there's 2 different forms of that equation given under the Fourier series coefficients section. There's ak e to the minus jk omega naught t naught, which is the one we're using. And it's equivalent to ak e to the minus jk times 2 pi over t times t naught. And you can use either equation. It depends on what you're given. So in this particular problem, we're given the fundamental period, omega naught equals 4. So we're going to go ahead and select this equation with the omega naught term. But if you're given your fundamental period of t, you can use the other equation. So now that we've identified that, let's look at time scaling. So given the properties table, we have signal x of alpha t, where alpha is greater than 0. So the reason we have that alpha is greater than 0 is we consider the time scaling and the time reversal as 2 different properties. So even though we have a minus 2t in this problem, we address the minus part of that with the time reversal step, and we address the scaling, which is the 2, with this step. So that's why we have the alpha greater than 0. And that's going to give us a coefficient of AK. So that's actually not going to change our coefficient. And then we have time reversal. We're given a signal, x of minus t. We get a coefficient of a minus k. So now we can combine these properties into one overall transform for our signal. And that's going to give us for x of negative alpha t minus t naught, we're going to get a coefficient of a minus k times e to the minus j k omega naught t naught. And we arrive at that by looking at these coefficients up here. And we see, okay, so when we shift our signal, we're going to get this coefficient. And then when we time scale it, we're going to get this coefficient. And the AK and the AK are the same here, so that's not going to change. And then we're going to have our E section multiplied through. And then when we apply the time reversal to the signal, we're going to get the A of k part of the coefficient transformed into an A of minus k. So that's how we arrive at the A of minus k e to the minus jk omega naught t naught. Does that make sense? Any questions at this point? Go ahead and type them in the chat or just shout them out.
Hi, can you
Yeah.
explain why you got the left side again?
So that's just the overall transformation we've done to our signal, just in
Oh,
general
okay.
terms.
Okay,
So
okay,
yeah,
thank you.
absolutely. All right, I'm going to keep going. If you have any questions, feel free to throw them in chat, and the other TAs will address them. So now that we have this, we need to identify what our omega naught and T naught values are. So our omega naught is provided in the problem statement as the fundamental period. So we're going to have omega naught is equal to 4, and T naught is in the time shift section. And we can identify that as our shift.
Would it be the
Okay, so in this case, because we are given the form for the property in x of t minus t naught, and in this case we have x of t plus t naught, we have x of t plus 7. In order to get that term, our t naught value actually has to be minus 7. Does that make sense? Any questions there?
Can you please
Yes,
repeat that
Raheel.
again?
Yeah, so when you look at our property from the properties table for time shifting, we have the form. I'm going to actually rewrite this equation so it's a little bit clearer. Give me just one sec. So we're given the form of x of t minus t naught, and this minus sign is important because up here we have a plus sign. So in order to make these, how do I say? In order to make it fit into our properties definition, our T naught is going to have to be minus 7. Does that make sense? Or do you need further explanation?
That makes sense. Thank you.
Okay. So we've identified our omega naught and our T naught. And we know that our new AK value, which I'll denote as A prime of K, is going to be equal to the original A equation with A to the minus K, E to the minus J, K, times 4 times negative 7. So now we've identified our equation for our new AK values, or A prime of K. Now we can evaluate that at K is equal to minus 2 and K is equal to 1. So we're going to get A prime of minus 2 equal to A of negative 2 times E to the minus J times negative 2 times 4 times negative 7. So we can go ahead and make this A of 2. That's the negatives cancel. And then we're going to get E to the, what is that, minus 56J. Because we're going to do negative 2 times 4 is negative 8, and negative 8 times negative 7. It's going to give us 56. Then we have a negative on the J. So we're going to get A2 times e to the power of negative 56j. And now we can go and evaluate our A2 term using the original equation.
Hi,
So we know,
Sorry to
Yeah.
interrupt. We have a question in the chat saying, how did we get 4 for W naught?
it's given in the problem statement. So up here, it's defined the fundamental period, omega naught is equal to 4. So that was just a given in this problem. I believe on the homework question, it's just defined as t. So you will leave your answer in the form of t. You'll have t as a variable. But for this instance, because we were provided with the information in the question, we can go ahead and set that equal to 4. So now we can go ahead and evaluate our A2 term using the equation up here. So we know
Hi.
that A, yes?
So I was wondering if so for A, since we don't have a calculator, can we just leave it as 4 times 7 times 2 on the test?
I think you can simplify that. I think you'll be expected to.
Okay.
I would, and I believe Dr. Cody Bakar is here, so he could speak a little more to this, but I would try to simplify as much as possible. And if you really can't, then just leave it. But I would try to simplify as much as you feel comfortable doing.
Okay, thank you.
Absolutely. So we're going to use our A sub k equation, and we're going to solve for our A2 value. So we're going to get 3 sine of pi over 3 times 1 plus 2 divided by 4 times 2 pi. So we can solve this. We're going to get 3 sine of pi over 3 times 3 divided by 8 pi, which is going to give us 3 sine of pi over 8 pi. And as sine of pi is equal to 0, a of 2 is going to be 0. So now we know our a of 2 value, and we can use that to solve for our a prime of negative 2. We're going to plug that back in, and we're going to get 0 times e to the minus 56j, which is just going to give us 0. So we know that a prime of negative 2 is going to be equal to 0. So that's our first step solved. Does that make sense to everybody? Any questions? Okay, I'm going to keep moving forward. So the second value we need to solve for is a prime of 1, which is going to be equal to a of negative 1 times e to the minus j times 1 times 4 times negative 7. So once again, we can simplify this to a of minus 1 e to the power of 28. We're going to get e to the 28j. And now we can solve for our a of minus 1 value. So a of minus 1, we're going to once again use our a of k equation. So we're going to get 3 sine of pi over 3 times 1 minus 1 divided by 4 times minus 1 times pi. This is going to simplify to 3 sine of 0 divided by negative 4 pi. And then sine of 0 is equal to 0. Therefore, a of minus 1 is also going to be 0. So we can go ahead and substitute that back in. And we're going to once again get 0 times e to the power of 28j. I'm sorry, this should have been a minus 1 up here. Or no, it should have been positive 1. Sorry, I'm correcting mistakes I didn't make. So we're going to get 0 times e to the 28j, which is going to give us 0. So once again, we're going to get a prime of 1 is also equal to 0. So that's part A of this question solved. Does anybody have any questions? Can also use bk instead of a prime of k. I believe that is fine, Jade. Okay, any other questions? All right, let's keep going then. So for part B, we're given the signal e to the 3j omega naught t x of t minus 2. So can anybody identify the transformations that are done to this signal and what properties we use to resolve it?
Time shift.
H.
Yep, so we do have a time shift. And then what do we do about this e to the 3j omega naught t in front? What property do we use for that?
Would it be frequency?
Yes, it would be frequency shifting, and I see it in the chat as well. Nicely done. So we're going to use our properties of frequency shifting and time shifting. So for time shifting, we're given a signal x of t minus t naught gives us a coefficient of a sub k e to the minus j omega, e to the minus j k omega naught t naught. And for our frequency shifting, we're given a signal e to the j m omega naught t times x of t gives us a coefficient of a to the k minus m. So now with frequency shifting, we do have an extra step as we have to determine what this m value is equal to. So the way we're going to solve that is we're going to set our equation that we're given equal to the equation on the properties table. So we're going to have e to the 3j omega naught t, and then we can disregard the time shift because we're addressing that in a different property. And we can set that equal to e to the j m omega naught t x of t. So now we can divide both sides by x of t, and that's going to cancel our x of t terms. And then we can take the natural log of both sides to leave us with just our exponents. So we're going to get 3j omega naught t is equal to j m omega naught t. So now we can divide over omega naught and t on both sides. And those are going to cancel. So we're left with 3j is equal to jm. And once again, we divide both sides by j. And we're left with m is equal to 3. So now we'd identified that. Now let's combine our terms. And we're going to get a prime of k is equal to a k minus m times e to the minus j k omega naught t naught. Any questions there? Do we understand how we're combining our coefficients and everything to arrive at our a prime of k definition? Okay, feel free to drop any questions in the chat again, and the other TAs can address them. So now that we have our a prime of k, we need to define some of the variables in here that we know. So m is going to be equal to 3. Omega naught is going to be equal to 4. And t naught, we once again have to identify. So our equation, x of t minus 2, we're shifting by 2, and it's already a minus. So we're actually going to take t naught equal to 2. So now we can define a prime of k as a of k minus 3 e to the minus jk times 4 times 2. So now we need to evaluate this at our two different k values. So we're going to evaluate at k is equal to minus 2 and k is equal to 1. So a prime of minus 2 is going to be equal to a of minus 2 minus 3 e to the minus j times negative 2 times 4 times 2. So this is going to give us a of minus 5 e to the, it's going to be 16j. So now from here, we go back to our original equation and we find a of minus 5. So we're going to get 3 sine of pi over 3 times 1 minus 5 divided by 4 times negative 5 pi. So now we're going to get 3 sine of negative 4 pi over 3 divided by minus 20 pi. Using the properties of the sine function, we can go ahead and pull that negative out. So we get negative 3 sine of 4 pi over 3 divided by negative 20 pi. Now we can evaluate that sine. And I believe that will be negative square root 3 over 2, but let me double check. Yep, so that's going to be negative square root 3 over 2 divided by negative 20 pi.
Right. If we just leave it as negative 3 sine over 4 pi over 3 over negative 20 over pi, could we just leave it like that?
I believe you should have your unit circles memorized, but I'm not positive. That is a question for Amulia or Dr. Cody Bakar.
I don't count.
Okay. So yeah, you will need to simplify farther than that. So you will need to know your unit circle.
I will say, oh wow, I will say if I were, I mean, this might be, yeah, this might be a question for Amelia or Vikram, but if I were grading, if you left it like that, I would be okay with it. Because like the point of an exam is to assess your understanding of the concepts. And if you kind of like have the main steps down, to me, that would be good enough. But yeah, I don't know. Amelia, what do you think?
Yeah, I think that's fair. Like, as long as it's a very simple trigonometric, like sine or cosine, it's better you solve it. But if something like 2 pi by under root 3 or something, then maybe not.
Does that answer the question?
Amelia, so is it yes? No, we
For
don't
the
have
basic,
to.
for the 0 degrees, 30, 60, 45, it's better you solve it. But for all other, it's fine if you don't like simplify it further.
Okay. So it
Good
sounds
thing.
like, yeah, it sounds like you need to know the first quadrant of the unit circle, and then you should be good for that. All right. So now we can simplify this a bit farther. So we're going to get 3 times square root of 3 over 2. And we can get rid of our negative signs. Divided by negative 20 pi. And we can multiply by 2 on the denominator to get rid of the square root 3 over 2 and just be left with square root of 3. So we're going to get 3 square root of 3 divided by negative 40 pi. And that's where we're going to leave that. So now we can plug that back in. We're going to get 3 square root of 3 over negative 40 pi times e to the 16j. And that's going to be our a prime of negative 2 value. All right. And now we just have one left to go. We're going to solve a prime of 1. So that's going to give us a of 1 minus 3 times e to the negative j times 1 times 4 times 2. That's going to give us a of negative 2 e to the power of negative 8j. So now we can evaluate our a of minus 2 term. That's going to give us 3 sine of pi over 3 times 1 minus 2 divided by 4 times 1 times pi. So now we can simplify that down to 3 sine of negative pi over 3 divided by 4 pi. And we can once again pull the negative out, get negative 3 sine of pi over 3 divided by 4 pi. That's going to give us negative 3 times square root 3 over 2 divided by 4 pi. So now once again, we can multiply the denominator by 2 and simplify
Ryan.
farther.
Sorry
Yeah.
to interrupt. We have a question in the chat saying, isn't it 4 times negative 2 times pi in the denominator?
Oh, yes. I don't know where I pulled 1 from. My apologies. Thank you for catching that. So it should be 4 times negative 2, which is going to give you negative 8. Thank you for catching that. So now we can multiply the denominator by 2. So simplify to negative 3 square root of 3 over negative 16 pi. Then we can go ahead and cancel our negatives. So we're left with 3 square root of 3 over 16 pi. Now we can substitute that back in and get 3 square root of 3 over 16 pi times e to the minus 8j. That is going to be our answer for a prime of 1, 3 square root of 3 over 16 pi times e to the minus 8j. All right. Does anybody have any questions about how we solve this problem, how to approach these problems, anything of that sort?
Can you just talk about like why, like how to put this like systematically, not like so like for example, the first step would be find the properties.
Yeah.
And
So the way you would approach these, so you're given a transform signal. The first thing is to figure out what transforms have been done. So for example, for this problem, we have a time scaling. Sorry, I should say for this problem, we have a time scaling, a time reversal, and a time shift. Then you identify the properties on the table and the corresponding changes to the coefficients. You determine your a prime of k equation based off of those. And then you just plug in your k values that you want to solve for, and you just solve out the math. So that would be the systematic approach.
thank you.
Absolutely. Any further questions? Okay, I'm going to go ahead and pass it on. If you have any further questions, go ahead and ask me in the chat, and I will do my best to answer.
Thanks, Ryan. Okay, everyone see my screen and hear me okay? How are we doing today, guys? Can I get a thumbs up to see if you're still alive after that problem? Are you guys alive? Hello? Happy Sunday, guys. Thank you for coming. Okay, only about 5 thumbs ups. 6, we got to 6, guys. Okay, Jade is barely breathing. All right, let's stop wasting time. Let's hop right in. So the outline of what we're going to talk today, at least for this problem. I'm going to be talking to you about Fourier transforms. So we're going to quickly go over some formula, a little bit of theoretical, not too much because you guys have an exam to worry about, but a little theoretical to remind you guys of why you're studying for this, give you some motivation on why it's useful. And then we're going to do 2 practice problems, okay? So Ryan just gave you a whole bunch of information about a Fourier series, right? And that's not the same thing as a Fourier transform, right? So when you're on the test, make sure to read things carefully because Fourier series is not the same as Fourier transform. Fourier just means, that's the guy who figured all this stuff out, but the word after it's the actual mathematical, property you'll actually use, right? So what Ryan showed you was you get a periodic signal. Let's just call it x of t for now. So this is a periodic signal, and you put it into this black box, right? And what you get out is a bunch of sines and cosines. And when you add these back together, you add these sines and cosines, you get your original your original signal that you fed into this black box, right? And these can be different frequencies. They can be different amplitudes, phases, right? So this is Fourier series, guys. This is not Fourier transform. Whoops, oh my gosh, I wrote the wrong thing. Testing you guys, Fourier series. Okay, so Fourier transform is very, very similar. So we can feed in a single signal to this black box, which we're going to talk about in a sec. Black box, okay? This can be periodic or non-periodic, guys. So it can be any signal. This applies to any signal. And what you get out is the frequency component of that signal. So you basically go from the time domain to the frequency domain, guys. Okay. So everyone feels pretty good about this, right? So we have a time domain signal, we feed it into this black box, and we get the frequency components, right? We lose all time information. So if, for example, you were to feed in a biopotential, let's just say in volts, right? Some random signal, what you're going to get out, so this is time, and what you're going to get out is a frequency component, which looks something like this, maybe, I don't know. Right, where this is frequency in hertz. Okay, and this is just, you can just think of this arbitrary amplitude, where it shows how much of each frequency is in that initial signal, right? So let's get a little bit into the formula, guys. So going to the slideshow. Here's the formula to get this x of jw, right? This frequency domain signal, this is how we get it. Right? So this is now our black box, and let's dive a little bit into it. So basically, we feed in our initial signal, right? Initial signal, and we get our output, right? That's easy. And then we integrate with respect to time, and we have this weird, e to the minus jwt. So you're wondering, okay, we're talking about all those sines, cosines. We're able to break any signal into its frequency components by breaking it into a bunch of sines. So what is this for? Well, this is the Euler's formula, right? So I don't want to get too much into this, but very briefly, feel free to message me or email me if you're curious. But then we break it into something like this, right? Right, so we multiply it. It's just like a convenient way to write sines and cosines, right? And the reason we do that instead of just multiplying by a any arbitrary why don't we just times x of t by sine, and then we're looking pretty good, right? Well, you thought so, but that's not true. So basically, this I component gives us information about the phase. So if this is your real and your imaginary, right? right? So if you don't have this component and you have a bunch of different lines, you're really only looking at like the projection onto this line, right? So depending on the phase, let's see different colors, so it's easier to see. Depending on the phase, you'll actually get a different Fourier transform. So it's important that we have this imaginary component. I don't want to go too much into it, but this gives us information about the phase, okay? That's why we don't just times by a sign. Why don't we times by a sign? Because we get information about the phase. Okay, so super quickly, and then we'll actually get into some practice problems. So how does this actually look? Well, you have your arbitrary signal, right? Let's use the biopotential example again. And basically, we just overlay a signal of a known frequency. So it's kind of like convolution, guys. You guys remember convolution? You'd have some signal, you'd flip it across the, we'll get to it later, but you'll flip it across this, right? And then you slide it along. You slide it along, stuff like that, right? So here, there's no sliding, but the rest is the same. So you overlay a signal, we can quote unquote call this a kernel. It's not convolution. It's different, but you can kind of use it to help you understand. You guys already understand convolution, so you can use it to help you understand this. There's no shifting or anything, but we can overlay this signal of a known frequency, right? We can multiply these together, and then add them, right? The integral, to kind of get the similarity for how much frequency is in our initial thing, right? So, for example, if this was maybe 5 hertz, so this is our x of t, guys. Lots of colors. And here's our x of jw. So here's our arbitrary amplitude. Just think of it as intensity or amount of frequency, right? So if this is 5 hertz, we can calculate some number for how similar these are by multiplying these together and then adding all the components, right? So we can do that. And then we can overlay, for example, a different frequency. Let's call that maybe 20 hertz. I'm not sure. And we can get a different number, right? And we get a bunch of bins of a bunch of different sine waves of a bunch of different frequencies. We get these bins and we just play connect the dots, right? So that's how this works. You know, you're actually in real life and you're measuring some biopotential, which when you're not in the classroom, maybe you're doing this on MATLAB or Python or something, right? You're going to measure this biopotential and you're going to loop through all these different frequencies and do this to find the Fourier transform, right? Okay, so that's enough for any questions in the chat?
Really, really quickly. I know when I was taking signal systems in undergrad, a really like common analogy or a really common example is audio. Like moving away from like the bio signals world. So like audio is basically a time signal, right? But each individual note is actually a sine wave of different frequencies. So like the middle C is, I'm looking at this now. Wait, no, hold up. No, sorry, middle C is 261.63 hertz. A is 440 hertz. And so those are all me screaming high pitch is high frequency. Yes, that is high frequency. And so if you look at the time signal of audio, it's basically just the sum of all these notes, right? The amplitude is the volume. The amplitude is the volume, and then the frequency determines the pitch. And so if you want to look at it in frequency domain, what you would have is the amplitude of each frequency. Yes, please scream silently, because you don't want to disturb other people. Sorry, this is for the people who are watching the recording later. This is all comments happening in the chat, which is what you're missing by not coming. Anyway, so yeah, that's I do feel like that's a more relatable example of time domain versus frequency domain in kind of everyday life.
Yep. And your ear actually does that. You know, that's how your inner ear works, right? It's able to separate an audio signal of different frequencies and then stimulate. It's like a little channel thing. You could Google it if you're interested. So
yeah, gotcha. But yeah, you can if you're interested, you can look up I think it's audio spectrum, I think is what it's called. And you can kind of it shows you like the amplitudes at different frequencies. And so that's basically frequency domain.
Yeah, and so signals has a lot of applications even outside biosignals, even for, how does your phone work? Well, it's able to break down the signals of your voice, and then it was able to send that packetting information to a different phone, and then it does an inverse Fourier. The other phone does the inverse Fourier transform, right? So it's able to replace some audio sound. So signals is everywhere, guys. So yeah, are we feeling good, guys? So that's the theory. Any questions on this before I move on to the actual problems? So this is why you're learning this, guys. Can I get a C of thumbs up? I'm gonna call on you guys if I don't get a C of thumbs up. Are you guys live? Oh, guys, 9 thumbs up. A 10. I'm gonna cry, guys. Give me a tissue. Oh my gosh, 13. Awesome, guys. Okay, great. So that's why we're doing this. And now let's do some actual problems because, this might, I'm not sure what the test looks like. We don't get to see it. This might help if there is some, conceptual questions, but more likely it's going to be like a math problem, right? So let's do some practice on that so you guys can do well in your exam. Okay. So we're going to go through 2 problems. Here's the first one. Okay. So the first thing you guys always want to do when you're given something like this, you always want to plot it. So it looks something like this, guys. So let's see. Let's arbitrarily call, let's call this guy y1 of t. And let's call this guy y2 of t. Okay. So here overall, we can just say some amplitude. And so if you guys remember this formula, that's going to be the first step, right? So basically what we can say is the overall y of t, which is this combined signal together. So we can call this y of t, is y1 of t plus y2 of t. Okay. So let's just start with y1 of t. So basically we can put both of these into the formula at once, but then it gets a little bit chaotic. So what we can actually do is just do 1/2 at a time, and you'll see a little trick at the end that I do. So if we just solve one, it'll make the second part way easier. So let's start with that. So as a reminder, here's our y1 of t. And if you have any questions, please interrupt. If I'm speaking nonsense and nobody understands, then we're all wasting our time, right? So if you're confused, speak up. Okay, guys, this is all the signals you need. Now it's calculus, right? So that's the signals. So let's go over the signals part before we do all the calculus. So we got the bounds here from up here, right? It was given to us. You want a highlighter, right? Bounds are from here. Up here is given to us. y1 of t, we know what that is. We're going to plug that in 1 second. This is from the Fourier transform, so that's just given, right? And then also from the Fourier transform. Okay, so now let's do the actual calculus part. So let's plug in y1 of t. Okay, looking good so far. So now we're in calculus, so let's just distribute this. And then let's separate the integrals, 2 separate integrals, guys. If I'm going too fast, please interrupt. I guarantee if you have a question, guys, you're not the only one with that same question. I bet a bunch of people have that same question. The only dumb question is the one you don't ask, guys. That's some philosophical advice from Will Knoll. I'm going to charge for that. Okay, so are we feeling good, guys? So now we're integrating with respect to t, right? So that means that this negative JW is just a constant, right? So we can just bring that down.
Yo, Will, can you scroll up a bit, please?
Oh, yeah. Oh, yeah, thank you. Okay, sweet. Are we feeling good, guys? Please interrupt if you have any questions. Okay, so quickly, this minus JW came from here, right? We're integrating. That's the property of e to the, AT. This minus 2 came from here, right? Okay. So,
Hey, Bill.
yeah.
Will we always have the E minus JW G
Yeah,
WT?
that's here's the golden formula. Yeah, good question.
Okay. Thank you. Sorry, I forgot.
Oh, no need to
That's
apologize. No need to apologize. You're all good. So the reason we don't have negative infinity to infinity here, right, is because we were given these bounds. So we could do, 0 to infinity, right? But it's just going to be 0. It's only defined from here. So that's how we got the bounds. And then the golden formula. Let's write that. Golden formula. And the x of t is just the input signal. So that's what we were given with here, right? It's our y1 of t in this case. And then this is always the case. This is like the property of the Fourier transform. Remember, this is how we get our cosines in our imaginary sine component. That's how we can multiply a signal by a certain frequency to figure out how much of that frequency is in our initial signal, right? Okay. So I think, did I skip a step? I think I skipped a step. So this should be something like this. Right, so first we have to actually incorporate these bounds, right? So we have to integrate with respect to t, so there's still a t there. And then we have a t minus 1 over minus jw.
Hey, Bill, can you scroll down a bit? I can't see what you're writing.
Is it hard to see on the Zoom, guys?
Oh, can you scroll down a bit? Yes, thank you.
Here is good. Okay. Right, so here, this is just this first half, guys. So we just did this. We just finished that. So now let's do the other half. Once again, this minus jw is just a constant. We're integrating with respect to t. Okay, and this part is just this part. Okay. So now let's just plug in our ones and our zeros. Okay, so I just finished this, guys. I'm rushing through it a little bit because this is just calculus. So in my personal opinion, I think you're not going to learn very much by watching me do calculus. I think you'll learn by doing it yourself and then comparing your answer with the actual answer and seeing if it's right or wrong. If it's wrong, you get to see where you messed up. So we already went over a lot of the signals. We still have a lot to go. So I would like to skim through this a little bit. So I'm going to rush. But if you're confused about anything, any of the calculus, please ask. I'm going to just assume you guys are feeling good unless you say something. Okay. Okay, so I just finished this guy. Okay, so this is basically, you've now basically finished your answer for this first part. So this is basically the answer for y1 of j1, but we're going to do some simplification, guys. So we're going to just simplify a little bit before we That way the next part will be a lot easier, okay? Okay, everyone feeling good? I just did some distribution. Okay, on to the next step, guys. Okay, just more simplification, guys. This is
Hi.
simplification central. What's up, Ruby?
How did you get J squared W squared again?
So here I just distributed
One.
this. So it distributed that guy,
Okay.
right?
Okay.
So this JW
Okay.
times this
Oh,
JW.
right. That makes sense.
Yep, and then if you remember the property, I think J squared equals -1. So that's how the sign flipped again from here to here. So now here is basically your answer, guys, but in order for it to, make any sense, you have to do some simplification. That way it's clean and it'll be easy for the graders to know your answer. So don't just leave it like this, but this is where the calculus basically ended, and now we're doing simplification. So if you guys, just to give you guys a reminder, this is only for y1 of t. So then we have to go back and do y2 of t, but it's a very quick thing. So once we do 1/2 of that, since they're symmetric, it's pretty easy for the next part. Okay. Yeah, guys, please interrupt if you have any questions. Okay. So here, just distributing the negative. And if you guys don't want to unmute yourself, you're more than welcome to type in the chat, or you can privately message one of the TAs or anything. We're here for you guys. Okay, so we're almost done with all of our simplification, guys. Now we're just combining like terms. Okay, and now these guys cancel. We get something like this. They either cancel or combine. Okay, so here's our answer for that first half, right? This is all for y1 of t. Don't forget that. So this is our y1 of jw, right? So if you remember here, this is our initial thing. So we can say this. So then this leads us to say, if we apply the Fourier transform, we can say that y of jw equals y1 of jw plus y2 of jw. And we just found y1 of jw. This guy's done. So now let's find y2 of jw. So we can basically say, you guys remember for our initial thing, that y1 of t is basically equal to y2 of negative t. So we can rewrite this as y2 of jw equals y1 of negative jw. Does everybody understand this? We're back to signals, guys. This is back to signals. So we can say that because y1 of t is equal to y2 of negative t. Right? So it's just the same thing applies in the Fourier domain, right? Okay, so now this becomes pretty easy. We can just essentially copy paste this almost, our initial answer here, and just substitute for negative JW, right? So then we get this. So looking here, guys, y2 of JW equals y1 of negative JW, which is equal to 2 times minus e to the plus JW. So basically every time there's a JW, you just flip the sign, guys. So here and here, okay? So then we can just add these guys. So our initial y of JW, and look here. So now we just plug and chug. Any questions, guys? You guys still alive? How are we doing? Let me know if you have any questions, okay?
I think I'm a little confused about why 2 of JW is equal to y1 of negative JW.
Yes, so looking here, guys. So here we see that y1 of t is equal to y2 of negative t, right? So we can say y1
Wait,
of t.
is it? One's
Yeah.
negative 2t plus 2, the other's 2t plus 2.
Yeah, look.
Yeah,
y1
it's
of
just
t.
minus t, so it is the same thing.
Oh, I see what you're saying. Yeah. Okay. Yeah. That makes sense to me. I would not have caught that at all. I would have just chugged along with the math.
Right. Are you feeling good, guys? It's a different color. I like green. Okay. So that's that little proof. And then we can just, not really a proof, I guess, but just a little showing that. And then we just apply the Fourier transform. So that's how we got this. So this is the same. Whoops. This is the same as what I just wrote, but in the Fourier domain, right? So then we can add these together here, and then we just do some simplification. So now we just combine like terms. So here, guys, we can simplify these guys to a cosine. So that's some Euler's. So here I'm going to write minus 2 cosine W over W squared. So how I got this cosine was from this property. You guys remember the Euler's? I think I'm not sure if this is a plus or minus, but equals cosine, right? So that's how I got this. So definitely you want to know your trig properties, your unit circle, your Eulers. Okay, long problem, guys. Are we still okay? Here's our answer. Okay. Can I get a see a thumbs up, guys? Did I put you all to sleep, or are you still awake? Are you still awake? Hello? Let's get a see a thumbs up. Okay, 6 people, 7 people, 9. That was less than before, but we'll still take that, guys. Okay, some of you are still with us. Hang in there, guys. Okay.
Well, can
Yeah.
you keep this for just a few more seconds? I'm still writing
Yeah.
down the final answer.
Yeah. So while
Thank
he's
you.
writing that down, to the other TAs, can I go on to the next one, or I'm nervous it'll take a while. Should we move on to the other things, and then at the end, if there's time, I'll just do the other one, and whoever wants to stay can stay, or how would you guys like to?
think it would be reasonable to move on, and then we can post work for the other one if we don't have time to get to it. Does that sound reasonable?
Yeah, I think that sounds good.
I
Yeah,
agree.
Is that good, Amelia? Okay. Yeah, let's
Yeah.
keep moving on, and then we can post the work for the second problem if we don't have time to come back to it.
So I'll
Yeah,
be
because my
posting this on.
convolution section is going to take a long time, so we'll see.
Yeah. And this work will be posted, guys, on Canvas. So just a little recap. Ryan talked about Fourier series. We can take a periodic signal, important that it's periodic. We can put it into this black box. We get sines and cosines. They can be different frequencies, amplitudes, phases. When we add those sines and cosines, we get our initial signal, okay? This whole problem was the Fourier transform. So not the series, but the transform. And here we can take any signal and we can get information about its frequency by multiplying it by sines and cosines and seeing how similar it is to the sines and cosines of known frequencies, okay? And so here's a solved problem. And so basically what I did, just found y1 of t, y2 of t, and you just plug and chug into the formula. And the bounds and everything you get from the problem. So the bounds I got from the formula, or from the given problem. The y1 of t I got from the given problem. And this, of course, is just from the formula. So that's a quick summary. And yeah. All right, so I'll pass it to the next person. Any questions before I go on? Okay. Thanks for coming, guys.
Cool. Thanks, Will and Ryan. Thanks for coming, everyone. I will be talking about the next part. Let me share my screen.
Wait, hold on. Am I going at the end?
Wait, is it yours or mine?
Oh no, she's solving a Fourier transform question and then it's your turn and then it's block diagrams.
Oh, okay. I didn't realize Alpha was also doing
Yeah,
was doing
mine
it.
is gonna be quick. I'll speed run it. All right, it's gonna be easy, everyone, for this part. Cool. Can you see my screen? Let's go. So will help us solve the first question of this one. And the next one, we're gonna talk about Fourier transform pairs. So as you can see, if we have signal here in this form, we can use Fourier transform and we will get the output in this form. So let's begin on solving our question. Okay, for this problem, find the Fourier transform of xt, where xt is sine omega naught t. So first step, oops, let me adjust this a bit. Okay, first step, psi omega naught t can be written in Euler form as e to the power of j omega naught t minus e to the power of negative j omega naught t over 2j, right? And what we want to do is we want to Fourier transform both of the side. So, and when we have like the Fourier transform, right, like this, we want to separate them into their own chunk. So instead, we have this.
Hi, Alpha. Are you writing something? Because we can't see it.
Weird. Okay, can you see it now?
Oh, what
Yeah.
the? It just like appeared.
Thank you. Oh my god. Okay, sorry, I just see. Thanks for telling me. Okay, so yeah, we can write. We want to like disintegrate our signal into Euler form. So we put sine in Euler form, and we're gonna apply Fourier transform into both of the side, and on the right hand side we will have this chunk, right? And 2j, spoiler alert here, 2j is just a constant, right? So I plug it out from the bracket, and I have 1 over 2j for a transform of e to the power of j omega naught t minus 1 over 2j f of e to the power of negative j omega naught t. Anyone have question on the steps? Can you still see my screen? Cool. So yeah, as you can see here, so this is the Fourier transform pair. So say if we have the signal that look like this, and if we use Fourier transform with it, we're gonna have something that look like this. Therefore, does AVE stand for Fourier? Yes, AD. I use this AVE with some signal in bracket is Fourier transform. Sometimes when you go on textbook, you can find like nicely drawn curve AVE like this as well, but I prefer to use simple F. Cool. Okay, so for the constant, we just leave it like that. But for this part, anyone would like to try? It's just simple here. It's basically this chunk here, the Fourier transform of e to the power of j omega naught t equal 2 pi delta omega minus omega naught. And that's for that part. And for this part, it's gonna be similar, but because it's negative, right? It's negative omega naught here. Therefore, instead of just being minus omega naught, it's gonna be plus. Therefore, we will have this chunk plus omega naught. Cool. And then I want to put everything in the same tidy order. So what I will get is 2 pi delta omega minus omega naught minus 2 pi delta omega plus omega naught. So I eliminate of that too. And what I will get is pi over j of delta omega minus omega naught minus omega plus omega naught. And that's it. And actually, I tricked you. This question, you can actually just look at the cheat sheet here. You see, yeah, we already have that solved there. I just want to show you how can we derive and solve similar question if you see on the exam. So basically, the Fourier transform of sine omega t, yeah, is actually the same thing we have here and there. Yeah, and that's it for this question. All right, anyone have a question?
I have a little more of a comment. So to give you guys a little bit of intuition about this, so sine omega t is basically one sinusoidal with a single frequency, right? So that's kind of why we get the delta functions. The reason we get two delta functions, so one is at minus omega naught and the other is at positive omega naught, is mostly because we can't tell the difference between positive and negative frequencies. but yeah, so it's kind of like a single note on a keyboard, right? So like A was 440 hertz, and so if you look at the frequency spectrum of just the note A, you would have a peak at 440 hertz. So it's kind of similar to this in that a sinusoid, or in this case sine omega t, is just one. It's just a sinusoid of one frequency.
Cool. Thank you, Teresa. Where did you get the first part from? Oh, I use Euler formula here. Yes, you. Let's see if I have that somewhere around here. So, Amelia, do you know if Euler equation will be on the exam?
It may not be on the exam. You may have to like remember it.
Yeah, okay. Everyone, put this down in your brain. Don't forget it. Remember it. Dream about it tonight. Yes, very important. This is the part where you need to remember. Where does this delta function come from in the derivation? The delta function is actually come from the given Fourier transform pair. So here, if we have signal, our signal here, when we put it in Fourier transform, we will have some delta function on that. Or do you mean in terms of like more theoretical thing? Why does it have to be delta?
No, it's fine. Yeah, I just didn't realize it came from the table. Yeah.
Yeah, I see. Okay. So let's say whenever you see this type of question, you should look at the table. Transform. And I believe it would be given on the exam. Yeah, it would be too cruel for you to remember these. Yeah, and that's it for my part. Can I go down? Let's go, Rui. All right. Give me thumbs up if you would like to move on to your favorite topic, convolution now. Ooh. All right, you're done taking note, everyone?
Yes.
Okay, cool. Then let's move on to next part.
All right, just to make sure it is my turn, right?
Oh, yes, it's convolution after
Okay,
that.
yeah, got it. Okay, no, you're right. Sorry, I got distracted by a chat from Will.
Yes.
Okay, so let me share my screen. All right, can y'all see? Chat.
Yes.
Okay, so I'm gonna kind of start by going over kind of a concept that I've seen a lot of people be confused about during office hours, and that concept is basically the difference between the difference between like how to find the different regions of the output and how to determine the bounds of the integral. And those are two different things, and I understand that it can be a little bit confusing. All right, well, what do I mean by that? So I'm gonna kind of I'm not gonna redo the whole thing because kind of look at use Alpha's recitation 3 question 2 as an example. I think she did a really good job on this question, but I also just want to highlight a few things that I think people might find confusing. All right, so I don't know if you guys remember, but this is what x of t looks like, and this is what h of t is. So x of t is just this triangle thing here, and h of t is a step function that goes up at t equals to 1. Now, if we do our usual flipping, so shifting and flipping right here, you get this for h of t minus tau. And then for x of tau, you pretty much get the same thing as x of t, but just replace the letter t with tau. And so let me flip to paint. All right, so this is x of tau, what I have here. And then what I have here is h of t of tau. It's just copied and pasted straight from Alpha's recitation. And let's see if this is a kind of helpful for you guys. So what I'm going to do over here is make a line diagram, if it'll let me. Well, that's what I had to do. Okay. Make a line diagram here, and this is for x. And what I'm going to do is mark. Let's make that a little bit longer. What I'm going to do is I'm going to mark down only the interesting points in this graph. So what does that mean exactly? Well, to me, the interesting points are kind of the bounds of these different regions. So we have x equals to 0, x equals to 3, and x equals to 6. That's a bad 6. And I'm kind of going to do the same thing for h of t minus tau. So to me, the only really interesting point here is right here at t minus 1. All right, now what I'm going to do is I'm going to do the usual thing where I kind of move h of t minus tau, and just kind of move that along. One thing to note is that wherever one of the lines in h hits one of the lines in x, I'm going to mark that as kind of like a significant boundary. And so I start over here on the very left, and I move along to the right, and I can see that this line meets this line. And so that happens when t minus 1 equals to 0, or when t equals to 1. All right, so let me go ahead and write that down. Deselect, okay. All right, now I continue, so I keep moving this along, and now this line hits 3, so that means that this another boundary of the output would be at t equals to 4, because t minus 1 deselect, and then yeah, and then kind of keep going. So move this along, and this line hits this, and so now we have t equals to 7. And so these are kind of like it's kind of similar to this, in that these numbers would be the corners of, or the corners of the boundaries of each section of the output. So then that basically means that the different regions would be t less than 1, between 1 and 4, between 4 and 7. Another thing, guys, is I don't have an iPad. So I'm writing on my computer, so yeah, my hands would be the different regions of the convolution output. All right, now let me stop here. Does anyone have any questions with this? Oh, there's like a bunch of chats. let's see.
There's no important question. I think you can just carry on.
Okay, sounds good. All right. Now let me get rid of that. And we have these for the different regions, right? All right, now to find the bounds of the integral. So, let's put that here. Sorry. All right. So then, and also if you look at the recitation, it should match. All right. So then, for t less than 1, I don't know if you guys remembered, but it looked a little something like this, and there was no overlap, more specifically, no non-zero overlap. And so we would move it along, and let's say if t is between 1 and 4, then it would look a little something like here. And so, oh wait, actually, I can just copy and paste from Alpha's thing. Okay, so integral is 0. And so from between t equals to 1 and 4, it looked a little something like this. So where it overlaps, it goes from 0 to t minus 1. And so that's where you would set the limits of the integral to. All right, so that's kind of what I want to stress, which is the difference between integral go from 0 to t minus 1. That's kind of what I want to stress, which is the difference between the bounds of the integral and these bounds. And let me know if that part was a little confusing. That was the t is being distracting. Sorry. Yeah, you are being distracting, William. You just had a chat that distracted me. All right. Anyway, okay. So this was for 1 to 4. Does it make sense to everyone that the bounds of the integral would go from 0 to t minus 1? Because that's where the non-zero overlap is. All right, so then let me just get rid of that and copy and paste in the other, the next section. So this next section is from 4 to 7. So it looks a little something like this. And you can also see here that the non-zero overlap goes from 0 to t minus 1. But the thing here is that it's in two different x of tau is in 2 different sections. And so you have to separate the integrals. And so if we were to separate the integrals, you go from 0 to 3. And you would have another integral going from 3 to t minus 1. And I think if you look at the recitation, Alpha's recitation, it should have this as well. All right, so continuing on, at t minus 7, you have something like this. And so at t minus 7, notice the non-zero overlap is what she has here from 0 to 6. But again, because it's 2 different sections of x of tau, you would have an integral going, you would have an integral going from 0 to 3. That's a 3. And then an integral going from 3 to 6. And I haven't bothered to write out the rest of it. But again, this is a recitation question, so you can go back and take a look. Is everyone kind of clear on this difference, like how to find these regions of the output, and also how to find the bounds of these integrals?
How do we know that it's split to 3? Oh, is it because it's going down after 3?
Yeah, so this is a completely different. Can you guys see my cursor?
Yes.
Okay, this is yes, that's because this is a completely different section from
Okay.
this. Like these are two different sections of x of tau. Yeah, so this is recitation, I should know this. Recitation 3, question 2. Thank you, Will. All right, so let me give you guys a completely different problem, and let's see if you can kind of do this process of finding the integrals, the integral bounds, and finding these different regions of the convolution output. So select. Okay, so the question is, here it is. All right, this thing, which looks complicated, but it's really not. So, all right, there we go. So this is the question. All right, so if we draw it out, we get if we draw it out, we get x of t. All right, so it's t times u of t minus u of t minus 7. So that means that it looks a little something like this, with this right here being 7 and 7. And then the next section is 14 minus t, going from t minus 7 to t minus 14. Copy and paste that wrong. There should be a close parentheses. And so it looks like this. And I'm gonna go ahead and just say this is x of tau, because all I'm doing here is replacing t with tau. All right, what about h of tau? So we're just gonna mentally replace all the t's with taus here. It looks a little something like this. 5 and 9. All right, does anyone have any questions with this part? Yes, since we're gonna post the homework 3 solution soon. There are a couple of issues I need to talk to that I've emailed people about, but we'll post that as soon as it's resolved. Luke, can you explain this one more time? What is this, Luke? The graphs from the equations. Can you repeat how I graphed x of t? Okay, sorry about that. So, okay, so this part is kind of looks like, I probably did go too fast. All right, so t just looks like a straight line like this, right? U of t, remember, is a square equation or a step function looking like this. And u of t minus 7 is a step function that looks like that, where that's 7. And so if you combine these two, you get a kind of a square function that has an amplitude of 1, and it goes from 0 to 7, right? This minus this gives you this. And then I just multiply t with this function. And that's this section of the graph. Does that make sense, Luke and Batul? Okay, and then it's kind of the exact same process for the second section, this section of the graph, right? So you have u of t minus 7 minus u of t minus 14. That gives you a graph for 14 minus t. We'll give you this section of the triangle. When in doubt, I like to check if the graph is right by using MATLAB. Yes, MATLAB helps. You won't be able to get MATLAB on the exam though, so it sucks. All right, so now that we have that, again, we do the flipping and the shifting for h of tau, and so we essentially get something like this. If we flip it, we get -5 and -9. That's bad. -9. And then if we shift it by t, you just add a t right there. And this is h of t minus tau. Let me check chat. Yeah, thanks, Amelia. All right, so is everyone okay at this point? Again, sorry for my really bad handwriting. I gotta use the mouse and keyboard. Is the function 0 outside of the triangle, or is it just the triangle? What do you mean the function 0? Oh, it's the function, the value of the function. Yes. So everywhere it's 0 everywhere else. Yes. Arena. That's what I mean. All right, so then let's kind of do that method of figuring out the regions of the convolution, right? So for x of t, can anyone kind of tell me what the different, what the like interesting points of, you can put the chat in different on my other monitors, so just keep it monitor. Can anyone kind of tell me what the interesting points of x of tau would be?
Zero, 7, and 14.
Yep, that's it. Thank you to whoever said that. All right, 0, 7, and 14. What about the interesting points of h of t minus tau?
T minus 9, T minus.
Sorry, there's like 2 people talking. Could you say that again?
T minus 9, T minus 5.
Okay, that's it. All right, now I'm gonna move this little line thing that I drew here for h of t. And let's see what happens. So again, we want to make a kind of a different region of the output when one of these lines in h of t hits one of the lines in x of t minus tau, or one of the interesting points. Okay, so let me move it along, and it looks like this one meets this one at t equals to, anyone?
It would be 0 to T minus 5.
Close. So it would, so the first boundary would be at t less than 5.
Okay.
So so the way I like to do it is like, all right, so we have this line hits this line at t equals to 5. So let me just someone write that down for me. Just 5. All right, and so if we keep going, now this t minus 9 line hits this line, and so at that point t equals to 9, right? Let me keep going. At this point, this line hits this 7, and so at this point t equals to 12. And if I keep going right, at this point t minus 9 hits the 7, and so you get t equals to 16. Keep going, and at this point t minus 5 hits 14, and so you get t minus 19, so t equals 19. And if you keep going, you get t minus 9 hits this 14, and so you get t equals to 23. All right, so to kind of write that out, the different boundaries are, deselect and then use brush. 5, 9, 12, 16, 19, and 23. And so then the different regions would be t less than 5, between 5 and 9, between 9 and 12, between 12 and 16, between 16 and 19, between 19 and 23, 23, and bigger than 23. 20 to T. All right, I'm going to stop here for a little bit. Did everyone understand that? And if not, what was unclear? And yes, this is a lot of regions. There's like 7 of them. Do you think you could draw the graphs just to see the overlap and visualize it better? I could, if that helps you, Jocelyn, then yes, you could absolutely do that. For me personally, I prefer to find the different regions first and then use the overlap to look at the integral, to determine the integral bounds, because I do want to separate, I do want to emphasize that those are 2 separate things. But now that you point out, Jocelyn, yeah, let's go ahead and do it, shall we? Unless anyone has any questions. All right, great. So let me go ahead and get rid of the stuff that we don't need. Don't need that. I do need that. Don't need that anymore. Let's move this here. And let me go ahead and get rid of this thing here. Okay, so we have these different regions, right? Let's start with t less than 5. So at t less than 5, at t less than 5, the graph h of t, if you kind of shift it, if you move it along, it's one of the 2 different buttons for it would be right here. You can't really make, how do I make that transparent? Well, yeah, it would be right here. If you want the actual graph that I made using Python, it looks a little something like this. So this is your x of tau, and this is your h of t minus tau. And so can anyone tell me if is there any overlap here or no? No overlap, that's right. So then the convolution at the integral at t less than 5 would be 0. Okay. Let's not delete that. Yeah. All right. How about for 5 between t equals to 5 and t equals to 9? Well, at between 5 and 9, this was just starting to overlap with this section, so it looks a little bit like this. Okay. I have the actual thing right here. So this is for between 5 and 9. And so then if you were to look at this, what would you say the bounds of the interval are? Anyone?
0 to t minus 5.
Mm-hmm. Yeah, because 0, and so we can kind of just ignore that. And so the integral, like that person said, whoever it was, is 0 to t minus 5 of 1 times tau d tau. Does that make sense to everyone? So I have the 1 here representing h of t minus tau. I have this tau representing, I mean, yeah, it's tau because this is the formula for this section of x of tau. I'm not going to work this integral out because we're short on time. We have like 5 other regions to do. But when I post my my solutions, I have this worked out in the algebra for that. All right, everyone good here? I'm gonna assume so. All right. Now for between 9 and 12, this h of t minus tau is right here. You want a nice pretty picture of it. It looks something like this. And so can anyone tell me what the integral would be for this one?
It would be t minus 5 to t minus 9.
Other way around, but very close.
T minus 9 to t minus 5.
Correct.
Okay,
Does that
and
make sense to you why, Ruby?
yes, would this be the full overlap then?
Yes. I personally don't think about it in terms of partial and full overlap. I just look at where does it overlap or where's their non-zero overlap. But yes, it would be.
Okay.
All right. So what would I put for the actual integral? Right. We did the bounds. What about the actual integral?
It would be the same as you did previously. It's 1 times t.
Right, exactly. So one yeah, thanks William. Sorry, I was reading the chat. Yes, that's correct. So at this point it's still only overlapping with this first section or the t section of yeah, this first section of x of tau. And so yes, you're correct that the actual integral will be the same. All right, moving on to the next section. We have going from 12 to 16. The graph looks a little bit something like this. And so does anyone want to try to find
Tarita, so we would have two full overlaps then?
Yes, very good. There are 2 intervals for this one. Good job, Ruhi. Do you want to try finding the limits for these intervals? Or actually writing out the integral?
Oh, okay. So, well, I was asking first, are these full overlaps?
Yes.
Okay.
But
so
I personally, so I will say I personally don't like using this partial and full overlap stuff because, as you can see in this case, there's several cases of full overlap, and so.
But I do think that it is important for them to like note it down in the exam. So maybe you could just like say that it's full overlap.
Yeah, but I guess like I just, you're not wrong. It's just like in this case there are like several different versions of full overlap.
I guess technically here I would argue that it's partial overlap, right? Because t minus 9, like it's fully overlapped if you if you look at the blue as one whole function, but if you break it up into the 2 plus and minus, technically it's partial, right? The
See,
t minus
that's the
9
thing.
to the
I
8.
barely see. I can see that as well. Like I barely know what partial and full overlap means. In this case, all I'm doing is looking at where's there non-zero overlap between the two functions. So I don't really care about partial and full overlap. I hope that's not too confusing, but I don't know. What do you guys think?
I understand, but if we need to write it on the test, I would rather know what full and partial overlap regions are there, so we don't get confused on the test.
Yeah, I mean, honestly, do whatever works for you. Do whatever works for you. But in the chat, I will say Jocelyn is correct in that the first one goes from t minus 9 to 7. An integral would be 1 times tau d tau. That is very correct, Jocelyn. All right, what about the second integral? Do you want to try, Jocelyn or Ruhi or anyone really?
7 to t minus 5.
Yep, good job. No clue who that was, but good job. And what would the function be? Oh, wait, really? It's important for the exam to understand partial and full overlap? Okay, I didn't know that.
Yes. Yeah.
Try again, Jocelyn. Almost correct. Let me point out this formula here. Or this part here. All right, well, no one's quite responding, but I will say the integral would be 1 times 14 minus tau d tau. Does that make sense to anyone? To everyone? This is this section, the second section of the triangle. Yes, I would agree with you, Jade. I was taught signals at a different university, and so this partial and full overlap, it's not a concept in my head. Does this make sense to everyone? Why the integral goes from 7 to t minus 5, and why the integral inside of it is 1 times 14 minus tau d tau? Okay, I'm getting a couple of make sense, so I'm just going to move on. All right, now for the next section, which goes from 16 to 19. That looks a little bit something like this. And so can anyone tell me what the integral would look like? Really, no one? I thought this was easier than the last region.
It would go from t minus 5.
Where's the left one?
T minus 9
Okay.
to 14.
Not quite. So this, I can't even draw a line. Like it overlaps like here. Pretend those are straight lines.
Okay.
Yep, Jocelyn. So it would go from t minus 9 to t minus 5. So t minus 5 of what?
One times, no, 14 t, 1 times 14 dt.
14 minus tau,
Okay.
right? Because
Yes.
because this section of the of the of all right, is everyone okay with that?
Yes.
Okay. All right, now for the next section, which is section which goes from 19 to 23. The graph looks a little something like that. Does anyone want to try to give me the integral?
T minus 9 to 14.
There we go. Y'all are getting it, I think, or at least whoever's answering is getting it really fast. So maybe this is useful. All right, T minus 14 of T9 of 14 of what?
1 times 14 minus tau. Yeah, Tip taught me before this.
Okay. Oh, it was 80 saying that? All right, good job. Okay, moving on. The last section, out of like these 7, I think this is the last one. Yeah, the last one is copy, paste. Paste. All right, what's the integral here?
And there would be no overlap.
Okay, yes, so the integral is
The integral is 0. And
there
then
we go.
into
Okay, yes, the integral is 0. So to summarize, there are 7, I don't want to believe. To summarize, there are like 7 different regions of the convolution integral that they go, these are the 7 different ones. And I kind of, or at least I tried to show you how to find the limits of the integral for each of these different regions. And I, again, would like to emphasize that finding these regions and finding the limits of the integral, those are 2 different things. It can be a little confusing, but hopefully, with practice and going through these examples and trying to understand it, hopefully that will help. Another thing is I'm going to be, so over here I have the solution for this whole convolution problem. I decided not to show you guys the algebra because that takes too long, and I mostly just kind of want to emphasize the concepts. But I have the algebra here if you guys want to go over it on your own. And I also have the final answer over here in red. It looks complicated as hell, and I'm pretty sure you will not have anything of this level of like complexity on your exam. But here it is. I think if you can do the more complex problems, you can do the one I use. So.
Hi, will this be posted?
Yes.
Thank you.
Yes, I will provide all these answers to you soon. Another thing I want to point out, so the output of a convolution, it's generally a continuous function and there are no discontinuities. So if you want to check your math, one way you can do that is kind of by looking at the boundaries of these different sections. And so basically what that means is that at t equals to 5, so like this first boundary right here, at t equals to 5, if you plug in 5 to t right here, it should give you 0. And same thing at 9. So at 9, if you plug in 9 over here, that should give you the exact same answer as right here. At 12, these values, or these 2 should give you the same number. At 16, these 2 should give you the same number. At 19, these 2 should give you the same number. And at 23, this should be equal, this whole thing should be, I just want to highlight, this thing should be equal to 0 at t equals to 23. Can I show the integral for 12 to 16 really quick? Yes, it is 12 to 16 right here. So the integral, it's two different integrals, because it covers these two different regions of x of tau. So the first one goes from t minus 9 to 7, and the it's 1 times tau d tau. All right, looks like you got the hang of it, Jade. All right, so I will be posting these. Hopefully my explanation made some sense, and I'm really hoping this doesn't confuse you more, because that's the exact opposite of what I'm trying to do. Can I go over one more time how to generally find the interesting points? Yes. Let me share screen again. Okay, can you see, who is it that's at that 80? Arena, whoops. Okay, so let's say that x of tau was this. So this was 7 and 14 and 0, and this is 7. And so an h of t minus tau looked like this, so t minus 5, t minus 9. So the way I do it is I like to just kind of draw out only the interesting points on a line graph, kind of like this, and just kind of ignore the actual graph for now. And the reason I do this is because right now I'm only trying to find the interesting point, like the boundaries of each different region. So for x of t, you have 0, 7, and 9, because these are the boundaries of the different sections of x of tau. And for h of t minus tau, the two interesting points to me would be t minus 9 and t minus 5. Because those are the boundaries of the different sections of h of t minus tau. And so what I do here is just kind of move it along. So so start from the very left and kind of move it along. So here you would have, let me do this. Let me move this over just a little bit. So it's more in the center. Okay, sorry. So start this at the very left, move it along, and basically whenever one of these interesting points meets one of the interesting points of x, that's where a boundary of the output would be. So you move it on to the right, and oh, it looks like this one's meeting this one. So then that's at t minus 5 equals to 0, or for t equals to 5. All right, and then all right, now let's keep moving this on, moving this along, and now this one hits this one. So then you get t minus 9 equals to 0, or t equals to 9. And then keep going. So move it along to the right, and now this line is hitting this line. And so you get t minus 5 equals to 7, or t equals to 12. So, and then keep going. So now this line hits this line, and you get t minus 9 equals to 7, or at t equals to 16. Let's see. Jade is saying she likes this number line method. Yes, absolutely feel free to steal it. I do hope this is more helpful. All right, anyway, so you get t equals to 16. Keep going. And let's move this along. And now this line hits this line at t minus 5 equals to 14 or at t equals to 19. And then move it along again. And t minus 9 equals to 14 or t equals to 23. And so these numbers are the boundaries of the different regions of the output. And so the different regions would actually be 1 and 9, between 9 and 12, between 12 and 16. Excuse my shit handwriting, guys. Between 16 and 19, between 19 and 23, and t greater than 20, 20, 20, oh my god, 23. There we go. All right, how is that, Arena? Does that make sense to you, Arena, or no? Okay, that's great. I will be posting the homework 3 solution really quickly. I think for homework 3 question this one, question homework 3, number 3, part 2, where you had u of t minus 2, and h of t is equal to e to the t u of t minus 3. That you can, I suggest you kind of try using this method for number 2. Let's see if you get the same answer that I did, and that could be practice for that. And that'll be it for me. It's way past 5. It's not way past 5, but it's past 5. So sorry, Alpha.
Yep, let's quickly go over block diagrams and then we shall leave.
Let's go, everyone. Let's speed run this block diagram. Are you ready?
Yes.
Oh, okay, let's go. Wait, not that one. Okay. Okay, block diagram, everyone. First step in solving block diagram. First step. You want to isolate YT from the equation. Isolate YT. How we do that, right? So I only want YT on the left hand of equation. And by doing so, I need to like rearrange my equation here. So after the rearrange of this equation, I'll get 1 over m xt plus k over m of x prime t, right? Which is actually derivative of x, and then minus n over m y double prime t. Okay. Anyone confused about this part? Okay, cool. Okay, now after we get this part, after we already isolate YT, the next step is to draw. Let's draw a block diagram. If you cannot remember what happens in block diagram, just remember this 3' thing. Remember that you put xt here, plus symbol in the middle, and YT here as an output. So to link our input to the output, let's examine what happened to the first term here first. So 1 over m of xt, and that's contribute to 1 of the part to YT. That means I want to add that, and when I want to include the coefficient, I simply just write it down over the line like this. And that's for our first term. Now the second term, k over m x prime t, which is the derivative of xt. I'll put this symbol here, and that means to derivative. And what I get out of this is gonna be dx over dt, right? And after that, it's not all of that, right? We still have the coefficient, which is k over m. And I will put k over m here. And boom, we're done with these two terms. And our last term, which is minus n over m with double prime yt, right? And that means we're gonna do derivative twice. It's gonna be like this, and what we'll get out of it is here double prime, double derivative with what's the coefficient? Negative n over m, right? And therefore we put everything in together and return that to y. And that's it, everyone. That's the end of speed run. How long did it take?
Like
Yeah.
2-3 minutes, less than 5.
Okay, I hit that first time point. Do you have any question or you need clarification on any of this step, everyone? I think this topic is very easy to understand. Therefore, it would be helping you in gaining the point on exam. So make sure that you can get this right. You can do it, and it's gonna give you easy point on exam. Okay.
So for just a quick question.
Yep. Is
Yeah. So